Okay, hello. Today we're going to be discussing the MCAT General Chemistry Review 2025 through 2026 edition by Kaplan. This is still chapter 1, 1.3, where we'll be talking about Rutherford, Planck, and Bohr. So, first things first, we got Ernest Rutherford. Here's a picture of him. And in 1910, he discovered that atoms have a dense, positively charged nucleus, right? You want to look more into it, it's called the gold foil experiment. So basically, the nucleus is only a small portion of the atom's volume. So what does that mean? There's probably going to be electrons. 11 years earlier, we have Max Planck. So in 1899, he developed the first quantum theory, which states that quanta is the energy emitted as electromagnetic radiation from matter. And the Planck relation gives us the energy of a quantum, which is the singular form of quanta. So here we have E equals HF. H is Planck's constant, which we will see frequently in this section. 6.626 times 10 to the negative 34 joules times seconds. The frequency of radiation is F, and that's how we will calculate the energy that a quantum gives. Fast forward to 1910, Niels Bohr combined Rutherford and Planck's ideas into the equation for the angular momentum of an electron orbiting a nucleus, where we have L, which is the angular momentum, equals n times h over 2 pi. So n is going to be the principal quantum number, which can be seen on the periodic table by these rows here. Right, so we got n equals 1, n equals 2, right? These are the rows. Here's n equals 2. This would be n equals 3, and so on and so forth. Again, we see Planck's constant, 6.626 times 10 to the negative 34. So that's going to be the angular momentum of an electron orbiting a nucleus. So the key takeaway here is that the further away an electron is from the nucleus, the more energy the electron has. So we have orbitals. When the electron is in the farthest away orbital, that's more energy the electron has. So what does that mean? When you have n equals 1, which is the first orbital, for example, hydrogen, let me change the color here. You got hydrogen and helium, right? The atom will be in the lowest state of energy, also known as the atom's ground state. So we got ground state, and if you get energy to the electron will move to a higher subshell, and it'll be called the excited state. Here's a picture of the excited state. We've got the nucleus right here, and these are the subshells. So this is n equals 1, and if you see here, energy comes in and moves the electron to the second subshell, which is n equals 2. Now we are in the excited state. So electrons, they jump from one orbit to another in discrete changes of potential energy. I use the example staircase versus a ramp, right? So in a ramp, you're going up, 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 up constantly. But in a staircase, you're going up in intervals. This is what discrete means, right? So discrete changes means you're going up one step, two step. There's a little jump in the energy levels. So here's a way to remember the important stuff for an electron. As electrons go from a lower energy to a higher one, they get ahead, which is what they absorb light. They get a higher potential energy. You can call them excited, right? The excited state. And they are further away from the nucleus, so they're distant from the nucleus. Electrons emit energy called photons when they go from their ground state to an excited state and back. So here's the electromagnetic energy of photons. So you got E is the energy, equals H, Planck's constant again. C is the speed of light in a vacuum, 3 times 10 to the 8th meters per second. And then you get the wavelength of radiation right here. So photons have specific wavelengths based on their energy transition, creating a line spectrum. So here we have an example of the different wavelengths based off of different atoms. We got hydrogen, helium, neon, sodium, mercury. And you can see, using this, we can figure out a fingerprint for the atom, because each atom will have its own specific line spectrum, and this is going to be the atomic emission spectrum. So when we go forward, So here we have different names for when an electron goes from an excited state back to ground state. So when the electron goes from n is greater than 2, so here's the different n's, right? These are the different orbitals. When it's going from n greater to 2, we got Lyman. So here it's going back to 1. This one's going back to 1. This one's going back to 1. Back to 1. That's Lyman. Balmer will be going from n greater to 3 to n equals 2. See, you see right here? N equals 2. This will be the Balmer section. This will be the ground state for, let's see, anything in the n equals 2. So lithium, beryllium, boron, carbon. That will be the Balmer state. And when we have something going from n is greater than or equal to 4, going down to 3, which is right here, this will be n equals 3. I don't know if you can see that with the yellow. That will be passion, or passion. I don't know how to pronounce that. So the equation E equals RH, 1 over n initial squared minus 1 over n final squared will give us the energy associated with the change in principal quantum number from a higher n initial value to n final. So right here you have the Rydberg constant. So R is going to be equal to RH. Rydberg's unit of energy is going to be this number here. 2.18 times 10 to the negative 18 joules over electrons. This will give us the energy associated with the change in principal quantum number, which you remember was the n values, and it's going from initial to final, right? Because we're subtracting it backwards. Usually you want to do final minus initial, but in this equation we're doing initial minus final because we want to know basically the energy of a photon. If you recall, I mentioned over here, photons give off energy when excited state electron goes back to its ground state. So just as there is a spectron of emission, there is also an absorption spectron, which is the measure of energy that excites electrons to a higher energy level. So you got energy going from ground state to excited state, and you got energy going from excited state to ground state. So depending on which one you're looking at, the spectrums will be different. So the cool thing about this is that the emission spectrum will be the inverse of the absorption spectrum. This is for hydrogen here. So they are the inverse of each other. The key takeaway is that electrons move from a lower energy level to a higher energy level through light absorption and vice versa. So that is basically what you need to know for this section of chapter 1.